Hey, hello everyone. So today's agenda is I want to write a square root function because, as you know, that's quite an important function for us to write. We usually use it for our mathematical operation, and of course, we're gonna use it later in future when we going to, write a global model. So that's the ultimate goal, however. But today's goal is that I want to write a square root function, and we see how we do. So, and during at any point, if you guys have any questions, just let me know. I will try to answer them, as usual. So yesterday's stream was a bit chaotic because I didn't know many things. I was doing live stream for the first time, but today I think I can do better. I attached the second screen, so I hope you guys can see things better. Let me share my screen. So from yesterday, I hope you guys remember that we wrote this main.cc file, which has our driver function, and here's we gonna test our functions, the mathematical functions that we write. And this cell.hh is our math library that we wrote yesterday. And in this library, I'm gonna write the square root function. Okay, so that's the thing. And to summarize what I did yesterday, the first thing we did was to write the pi function, which is just this constant value 3.1415 and so on. And this I took from this website. Then this two function is first function is actually mod function. It's self-explanatory, right? And the second one is sine function. It will return the value of the input, which is x. Factorial function we also wrote. Then this is the GCD, greatest common divider, and MSB, most significant bit. And last thing we did was write a power function. We dealt with the integer powers. For example, if we have a powers of 2 or 3 or any integer number, or even -2 or -10 or something like that, then this block of code will handle the things. But the thing we didn't do was, what if it has a fractional part, which is 0.45 or square root? So this is something we're gonna do today. We're gonna write this part of the power function where we handle the fractions. So today we will have some theory discussion as well. So I will share a whiteboard at some point so that you guys can understand what I'm actually doing. Otherwise, it would be a bit hard to follow. So what I'm gonna do is I will write some code first, and then I will explain it on the whiteboard. So let me first remove this return 0. White permission. Yeah. So now, since we are into the fraction part, we first write if we have a negative power. And currently, I don't think I can handle the negative power because it has imaginary roots, etc. So I'm just excluding that possibility first. So let's say nth root of negative value is not allowed. So this is currently a limitation which I think in future we can handle, but the goal, my ultimate goal is to write a global model for nuclear collision. So I don't think for that I need any imaginary numbers in my simulations. So I will just return 0. For your understanding, let's say I'll just give you an example. Let's say if I have a negative 2 and I have a something like negative 2, then this is a bit of a problem because oh sorry, it's like a, if it is like this, then it's a problem because we can't have a negative square root. It's a imaginary value, right? So that part I want to avoid. So this two lines of code will handle that. Now, if our fraction part is not negative, then what should we do? We first, as I wrote yesterday, we are dividing our power, which is of n, into two things. First is the integer value, and the other one is the fraction value. So the integer part, we can directly deal with them with integer power. For that, const double x int power part power x raised to n sine multiply by n int. If you guys have any questions, just please let me know. Now starts the fraction power. Now be attentive of what will gonna happen now, okay? Because this is quite an important part of this code. So const int p big is equal to integer power. VS Code always corrects things which I don't want. Allowed error. And then I also want the denominator part to be a whole number. So big int, then 1 divided by allowed error. So if I have a fraction part, then this block of these two lines should convert it into the integer value or close to integer value. Okay, and then const common divider, which will be given by our GCD function, which we wrote yesterday. So now what we're gonna do is we're gonna remove GCD from our fractions. So to remove common divider, we write const double p is equal to p big divided by common divider. Const double, similar thing for the denominator. So q big divided by common divider. Okay. Once we do that, we dwell into the actual part. So now I will go into bit theory. So first let me write the part where I need these things so that I can discuss things effectively. So const double, I will explain what I'm doing here. Just wait for me to write these few lines so that I can connect it to theory later on. And this is our initial guess for our square root. And this is from binomial. sorry, binomial theorem. Okay, and what's our initial guess? Our initial guess is 1 plus and sine, and sine is the sign of our power, and then power for x multiplied by our fraction. Okay, so double x1, and this is our second guess, which I will explain. So at this point I will explain you guys what I'm doing, and for that I need a help from Wikipedia. So let me share the screen. So here, let's say this is our nth root of any system. So I'm gonna use this formula, which I'm going to code. So let me give you the example and share my whiteboard with you guys. Wait a second. Yeah. So here, yeah. So as I said, in general, if we have 1 plus x raised to n, where mod x is less than or equal to 1, and in our case, n is also equal less than 1. Sorry, right? So we can approximate this thing to 1 plus nx. Make sense? So this is a very gross approximation which I will use in my initial guess. So let's say, for example, if you have a square root of 2, then according to this formula, what will happen is 1 plus 1 is 1 by 2, and in this case it is approximately equal to 1 plus 1 by 2 into 1, which is 1.5. Okay, so this is a very gross approximation of square root of 2, and we are quite happy with that because, as I said, it's an initial guess, and we will do Newton's bisection method to make it more accurate. But for now it is okay if we just use this approximation, right? So yeah, let me remove this whiteboard, and we can now, I think, proceed with the coding part. So this was this formula, and as you can see here, that's exactly what I did. Okay, so this line is basically this formula with only one term. Okay, so that's one-to-one comparison. Now our goal is to make it more accurate, right? So for that we need to use this Newton's bisection method, and as you can see, there are number of iterations which will give us more and more accurate answer. So I'm just going to do this. At any point, if you have any questions, guys, please comment it. I would be really happy to answer it. Otherwise it can get a bit complicated, and I would be also happy to chat with you. So that's the thing. Now let me go the Newton's bisection part. Now, since it's a constant expression, we need to have some limit to how many loops we have. So for that, I already defined the maximum loop in my function, and I will write max iteration is I, or maybe I should write, yeah, I plus plus is okay. And now I will use Newton's bisection formula, which is 1 upon q. I think it would be helpful for you guys if I just, divide the screen and you can see it more clearly what I'm coding. So I'm coding this formula, okay, here. So you can have a reference to what I'm doing. So 1 upon q multiplied by, in our case, n is q, so you guys cannot follow in that way. Q minus 1 multiplied by x0 plus x divided by power, power of x0 q minus 1. Make sense? So this is what we are doing. Then I can also give you the link here from Wikipedia. You can copy this and yeah, Newton's method. Okay, so double error is equal to mod double x minus x0. So basically what I'm doing is I'm comparing the new value with the previous one and see how much error I'm having. Okay, and that error will help us to terminate this loop early. So if allowed error is greater than the error of our iteration, then we can just return the value and come out of the loop. Power part multiplied by power x1 and sine multiplied by p. Okay, so that's the thing, and we shouldn't forget this next iteration. Let's say if we don't have an early termination, then we need to return it once we complete this entire loop, right? So for that, we need to write the same thing again, which is this line of code. Yeah. So same thing. And let's say if we have some error in our code or something, then this return 0 is our fail safe. We will at least have 0 to test things, So that's the thing. Let's see if it works. So now what I will do is make clean, and this should remove all the previous things, previous binary files, and now it's a power. Let's say 2 raised to 0.5, which is square root of 2. Let's see what's the value we get. So let's make, okay, and let's say out point. So 1.4142, which is quite accurate and what we expect from our square root function. But this function is quite general. As you can see, if you have 3.5 power, then also you can make clean and then make again, and then it will return the value. Okay. Usually in our math library, we also need a quick functionality to square root function. So in that case, what I will do is I will just take this code and write another function, which would be square root. And since we already know that it's a square root, what we gonna return is power x 0.5 and whatever the max iteration is and whatever the allowed error is. So this should return the square root of any number. Let's see if we can have the square root of 4 here. Let's see what we get. Square root. So let's make clean and now make and see. Yeah, so square root of 4 is 2, and we can even go to any fraction number. Let's say square root of 2, then again we need to make and make again and out bind. So square root of 2 is this number as we expect. If you have any other number which you want to test, just let me know in the comments. I will wait for a few seconds. If not, then I will proceed. So meanwhile, I can also test some, let's say 50 and make clean, say make. So out. So square root of 50 is this number, and we can also check with our favorite root library sqrt 50, same as what we expect. This one is a bit approximated because it's a printing thing. So that's the thing. So with this we finish our square root thing. The other thing I want to write is I want to write a function which returns the combination of numbers. So for that, sorry, before that, I want to write a function for exponential. So exponentials will gonna be very useful for us. So it's quite essential that we have this const expression double expo const double x const unsigned long max iteration, it's equal to 1 plus 4. So, and then we also need to give allowed error, and the default value I have set to 10 raised to minus 8. It's quite reasonable. So once we have that, what we can return is return power. I also done this thing. Value of exponential I already got for you, so that I can copy and paste. And x would be the power, max iteration, and then allowed error. I also need to divide the code so that it looks good. If you have any questions regarding syntax or method, just comment it. It is also great for you to learn few C++ commands, So let's keep it more educational and two-way communication. So this is the exponential function. Now I also want to write a combination function. So for that, I can go to my factorial function here, here, and now it's quite straightforward, right? So we can even search on the Google combination of numbers Wikipedia. So yeah, here. And what I want to do is basically I want to code this formula. Okay. So so that in case if we have any binomial expansion and we want to go to nth order, we can use this formula. So for that, let me divide the screen so that you guys have a reference. So I want to code this formula, and for that I will just write const expression double combi. Then I need only two input, which is const double x, const int n, and then I want to have if 0. So this is the identity of our combination, right? So in that case, return 1, otherwise else if 1 is equal to n, then you should return x. And now comes the iterative formula. So else in that case you need to iterate, which I can write as this function n plus 1 multiply by combi x n minus 1 divided by 1 into n. I'm multiplying by 1 to make it fraction, to convert n into double basically. So this should give us a combination, and if you want, let's try some numbers here. Combi, let's say 5c2. What should we get? Let's say make clean, make. Now out is 10. So it's correct, right? Because 5c2 is basically 5 multiplied by 4 divided by 2. So this will give us 10. So our function is working. Now, let me minimize this window. So I think we have our math library. If you guys have any questions, just let me know. So with this, I'm finished with the writing the math library. And I know that some functions we can write, for example, sine, cos, tan, or other trigonometric function. But the simulation that I want to do, which I'm targeting, may not require this. So for now, I'm just not worried about that thing. The next thing which I want to do is I want to write a function to model the nucleus. So now I will shift gears to more physics side. Math part is done. So include, let me make a file name nucleus.hh, and yeah. So first thing we do always is write a pragma once so that our compiler doesn't get confused. Now I want to make a class. Yeah, this autocomplete feature I really but it's not entirely useless. Let me just remove this. Yeah, for now this is okay. Do-do-do-do-do. Now, what are the properties of nucleus? So for the properties of nucleus, we know it has a number of z number of protons and n number of neutrons. So for that, what we do is write a template with int z, and we also need total number of nucleons, so it's just a. From this, what we can write is this, that int, I should write const int is say a minus c. So n is number of neutrons, z is number of protons, a is number of all nucleons, which is protons and neutrons combined. Uh, oh, I'm sorry, man. I was just into the coding part. Sorry. So, do you have any questions? I am really sorry I was not reading your comments. Uh, let me write something. Hello. I If you have any questions, just let me know, man. I'm really sorry I didn't look into the chat. Let me give a bit of a break. I'm also a bit tired of speaking too much. Ah, so yeah, so if you joined recently, I just wrote this square root function, which is the title of this live stream. So from here, you can follow what I just did. And this square root function is basically calling this giant power function, the theory I just explained a few minutes ago. So that's something. And now what I want to do is I want to create a global model. If you guys are not aware of what global model is, let me quickly show you guys what it is. Global model. So it's for the high energy collision. I wonder if we have any Wikipedia for nucleus collision wiki. I'm not sure if we have any. Yeah, we have it. Thank God. So my next goal is basically to create code for this thing. Since I wrote everything from scratch, the math library, we should have we should be able to code this formula in with our math library. So that's the ultimate goal. Uh, so yeah, but I think coding this global model will take some time, but my current goal is to just write a functionality for us to have a math library, and also want to have the nucleus modeled in the code, because that's the baseline condition in the global theory, that at least I need two nucleus which are about to collide. So that's the ultimate goal. But first, I just want to create the class for the nucleus. And once we have that, we want to have a functionality so that we can get number of protons and number of neutrons from this class. How to do it? So const expression, we need const get z, and this will return we need to tell the compiler that we are not messing with the private members. Okay, so that's why I have this const uh, flag, so that my compiler knows, and return the first. And why is the square root function so complex? Is this high level coding? Yeah, so the square root function is like uh yeah, so here is the square root function I just finished coding. And usually it's nice to know how to code this square root function, because sometimes what happens is the game engines or any other engine that you use, they have some built-in function for square root. And there is no let's say straightforward way to calculate square root with desired uncertainty. Therefore, what we have to do is we have to go through multiple operations. As you can see, this is a big function, and what it can do is it can slow down your code. So I remember I was watching one video, and in that, the guy explained that one game engine faced a lot of problem because they have a bad square root function written. So they had to optimize it. So if you have to face this kind of a task, then it's better to know how to code square root function, right? So that's my intention behind this square root function. It's one of the intention actually. So if you guys can have this kind of a function, then I think it's well optimized. Of course, there is always a room for optimization, and yeah, you can further optimize if you want, but this is what I wrote for my function. So that's it. I hope I answered your questions. Vishnu Arjun, I hope you this answers the questions. So that's the thing. And I want to return to this nucleus part. And yeah, so this will return the z value. And I also want get n, which is the number of neutrons. Const, can you explain the code quickly? Yeah, sure. So, uh, first of all, the entry point for any C++ code is the main function, which is a driver, right? So, in this driver function, I have my test function, but the main file, which is a library, is this cell.hh. And if I go into it, this is what you have. So here I have all the usual function that we use. For example, value of pi. Let's say if you want to take a modulus of the number, then this function will do it. If you want to know the sign of the function, and other functions like factorial, combination. And down here, I have the power function where it can do the square root and other complex things. And if you want to see the example of a square root, then let's say square root of 2, right? So what it will do is, to execute the code, you need to make clean. Sorry, I need to go back first. Make clean and make, and this will print the square root of 2. So that's basically the summary. And if you want to know what this make is, you can have a look into my make file. So this is a pretty standard way if you want to handle any big C++ project. So if you have any questions regarding makefile or any this math library or anything, just let me know. I will try to explain it. Okay. So that's what I'm doing. And now, as I mentioned, my ultimate goal is to create this global model inside this C++ code, because I found that things are the code that exists can be optimized further and I can do better. So that's why I'm modeling the nucleus, and at some point we will also model the global model. So that's what's happening overall. I hope it answers your questions. What's your name? Pistoli. Yeah. So return. Uh, Making a spelling mistake. And I also want constant expression int get a, which is our nucleon number, const return a. So at this point, I think I should check if things are working as I expect. Otherwise, I will just blindly code and make mistakes. So let me first include nucleus.h, and what's it? Yeah, nucleus, not null pointer. Nucleus. Let's say it's calcium 48. Then let's say it's 48 calcium, like this. So I'm not expecting anything to happen, but at least I'm expecting a smooth execution of the code without any errors. So that's the test I want to run first. Make clean. Let's make. And let's run the binary. Okay. So things are okay-ish. Now, so this math library part is already done, so I'm just closing it. I think I'm okay with this. Yeah. So what is this function do? So this nucleus, you mean? Basically this line, or you are talking about this line? The square root one, right? So the square root function basically calculates the square root from the math library which I just wrote. So what it will do is, once I call this function, oh, nucleus, I'm sorry. So nucleus is not a function, it's a class. So let me make a divide. So what it will do is, nucleus has two properties. One is number of proton. This is the actual nucleus I'm talking about. So it has a number of protons and number of neutrons. And this class, what it will do is, it will take z as an input and weight of the nucleus, and from that it will determine the number of neutrons, which is basically a minus z. So once I have that, I will add further functionality into this class so that I can, make a detailed global model calculations. So does that make sense? Uh, do you want to know more about this template, or you just wanted to know what the nucleus is? I hope it answers your questions. I hope you can ask if you want. Okay. So once I have this, I want to add some functionality to my nucleus. Okay. So what I will do is, um, I want to have a density of the nucleus, because that's the one of the inputs in our global model, in our global theory. So for that we need, what do we need? Const expression. We need a double get row z. So what I will gonna have is, I will get the density of the protons from this function. Let me open my notes so that I just don't go astray. So that. Any questions, chat? Me as I open this my other notes, and I also need a little bit of break. I'm speaking too much. Ah, so I am also planning to upload this code on GitHub at some point. Oh, I'm really sorry. I also need to what's so the question is, what protons have to do with the square root. So actually, I did not mention this in the title because I thought I won't be able to code square root function in 1 hour, but apparently I coded it. So let me explain what my ultimate goal is. So the ultimate goal of this series of live stream is that I want to code this global model. Okay, and what this global model you is basically, let me share my screen. Wait a second. Yeah. So where is my screen? Whiteboard. Yeah. So let me clear the page. So the ultimate goal is global model. Now there are codes that are available to do this global model calculations, but as I said, they are slow, or I'm not happy with that. So to code this global model, what I did is I wrote the math library in C++ from scratch. And that was the goal of first live stream and half of today's live stream. Now I'm shifting my focus to more the physics side. And what this global model does is, let's say if you have a one nucleus which is moving with nearly the speed of light, and there is another collision sorry nucleus at target. Let's say it's a target nucleus. So what we'll do is, at some point, this projectile nucleus will collide with the target. Okay, and this is the axis and this is the direction of things. So ultimately you will have some kind of a scattering, and from this scattering you can have the global model calculations. And this is my ultimate goal, if I am clear. So this formula, as you can see, it has a lot of math operations. So my ultimate goal is to code this formula, and that's where the square root functions come into the picture. And that's how I think how nucleus connects with the math operations, if I was able to explain it. Yeah. So I think if it gets too complicated, then I can maybe just leave this thing for the next live stream, because I think if people joins, then they may have a lot of questions. So maybe I can just give a rest to this idea. Meanwhile, maybe we can do some fun stuff. Let's write a Fibonacci numbers in our math library. That would be quite fun to do. Fibonacci sequence wiki. Hmm. Yeah, here. So Fibonacci numbers start with two initial numbers, and then we can iterate it over this function with this recursion function to get nth number. So let's try to code this with constant expression library. So mm, this is very complicated. I think the simplest approach is to make square root with a Taylor series. Oh, yeah. So I don't agree with that, because I will just explain why that is the case. And by the way, I already considered the Taylor expansion. So here. So if you look at these two lines of the code, then what I'm doing is I'm practically taking the Taylor expansion, but I'm only considering first term, not the nth term. Okay, so why I'm doing this? Because let's say if your x is greater than 1 in this Taylor expansion, that is the must condition, that your x should be less than or equal to 1, right? So in that, so that's the limitation. But in math library, we want a general square root function that can take a square root of any number, right? So what I'm practically doing here is I am making an initial guess from the Taylor expansion, because it's still valid. Okay. It will start to diverge if I include higher order terms, if your x is greater than 1. Once I have the initial guess, I am considering a Newton's method, which converges with greater speed compared to your Taylor expansion. Okay, and in this Wikipedia article, you can see that in just 5 iteration, it can consider it can calculate square root of 34, not square root, it's a fifth root of 34 up to tens of decimal places. So that's exactly what I'm doing. Once I have an initial guess from Taylor expansion, I'm iterating over this Newton's formula to get my nth root of any number. Does that make sense? I hope I was able to explain uh, the methodology. Yeah. So that's code Fibonacci number. And if you have any further questions, just let me know. You can even take a screenshot of this function if you want, and if you want to ask questions later. Okay. So this is the part where it take calculates the nth root of any number. Any number means, of course, with this restriction, we can't have a negative nth root of negative values. Otherwise, sometime it can give you. When you use the Newton method, you will use square root part. No, actually. So here's the power from. Let me go back to here. So the advantage of Newton's method is that if you want to take a nth root, let's say 1 upon 2, right? Then that denominator comes into numerator. As you can see, uh, this is basically formula to calculate nth root. Maybe I can explain it. Mm, wait a second. I need to give my whiteboard. Yeah. So there. Maybe standard way. Yeah. So as you can see, this is the nth root of any positive number, right? So let's say we want to take a square root of 2. Okay. So according to this formula, what we have is 2 raised to 1 upon 2. And if we compare this thing with this formula, then our n is equal to 2 and x is equal to 2. Or maybe I should take some other number. Let's say 5. Okay. Let's say it's a 5. That's 5. So now maybe you can understand it. So let's define this thing. And through which initial guess. So where a can be root of. Oh, I'm sorry. It's not x actually. This one is. Where is my eraser? Yeah. So this one is basically a. So what will happen? Let's say this is some value x. which we don't know, right? So x k plus 1, k is the number of iteration, and xk would be xk raised to n, which is in our case it's 2. So you see, this number which was in the denominator is now in the numerator. So you are not taking any square root in the Newton's bisection formula, right? So that's what's happening. And let me write this formula in full length. So this k and n minus 1 is basically 2 minus 1, which is 1. Okay. So I wrote this formula, but you can easily translate it to this formula because it's a matter of taking some numbers common. I hope I was able to explain, right? So that's what's happening here in this function. So here, makes sense, man? Thank you for asking lots of questions. At some point, I was feeling that I was doing things alone, but if you ask questions, I'm really happy that you are taking interest. Hello. So, happy to answer any questions. I'm happy that you are interested. And this technique, I was quite happy. Why are you doing this? Yeah, so I explained in the stream. So, first goal is, of course, to learn things, And if you watch any videos from a game developer or any uh, other senior engineer, they will always tell you the story about how they coded square root function. The reason is square root function is quite useful when it comes to model the direction of your world in the game. Okay, and depending on how many operations are involved in the square root function, it can slow down your game or any code, or it can give you the bad experience. So if you want to optimize some functions in your code, then it's better to write square root function from scratch. Let's say right now my ultimate goal is to create a physics model, which I will do in the next live stream. But let's say if that's not your goal, then what you can do is you don't have to do this Newton's bisection part. As one of the um, viewer said, I can just take a Taylor expansion, which is the just this one line, and have a very fast function which takes the square root. Okay. But if you want to do some accurate calculation, you can always do Newton's method followed by Taylor expansion. So that's why I want to do this exercise. And I also want to, share some of my coding skills and share my knowledge. Oh, you want to know about me? So I recently complete my PhD degree in physics, and currently I'm just enjoying this kind of doing this kind of a live stream. So that's what I'm doing. 5 years ago, I used to make a videos in Python, but now I shifted my focus to C++ because I found it more enjoyable. But of course, if you have any questions related to Python, I will try my best to answer it. Thanks for asking questions. Okay, square root function. So, yeah, I was saying let's do some fun because Fibonacci numbers are always fun to code. And it's a very short recursive function, so we should be able to do it quickly. Yeah, so how to do it? So just write const expression. By the way, you guys know what this constant expression is? You can ask me if you want to know more. I'm currently learning DCA in C++ and wait, side by side. Oh man, I'm not sure. The reason I am not able to answer this question is I don't have any formal education in computer science. I have a formal education in physics, so I'm not sure if I'm a qualified person to answer these questions. Whatever I learn, whatever you are seeing here, I learn from the YouTube or online tutorials. But if you have any questions related to C++, just let me know. I am happy to answer them. Into. Yeah, so I'm going back to Fibonacci numbers. So let's do int and write Fibo. Or Fibonacci would be too long. Hey, can you give my GitHub page a lock? I'm not sure. You mean look? I don't have a link to your GitHub page, man. So, Fibo. Yeah. So what we need is basically we only need two numbers, right? Which is initial guess and the next guess, and then it will just iterate it over. So let's write const int f0 and const int f1, and what do we need? We also need a limit how many numbers we want. Okay, so how to do it? We can have const unsigned long, very max num, and or do I need it? Yeah, I don't think I need it. I think we can do it later. And what we can return is f0 plus f1. Okay. Is it optimized way to do it? Let's do. So yeah. So let's write a for loop, and let me just remove this bar. It's not. Any new viewers, If you have any questions, just don't hesitate to answer. Sorry, I'm fumbling. Just don't hesitate. Ask any questions. I less than maybe 5, I plus plus. Uh, then what I need is I need to print cout cell. Not this one. Fibo. Then I need I and I plus 1. What it will do? Or I need to write it here, so I think I need a maximum number. Unsigned long. Maybe I also need a const here. Then unsigned long max iter. Okay, max num is better. So I need to migrate this part of the code from here to here, and I think I don't need to return anything, so I just write a void. This should be max num, and then I can do I have f0. Are you guys following anything? I suddenly went stress. So what I will do is I will print f1 is equal to f0 plus f1, and then sorry, I also need this should be this should be this, and then I can basically print numbers. stdcout to f1, and I need a next line during the print. Okay, so let's try this function and see what we get. Cell fibo, and then we can have initial guess 1, and then how many numbers we need? 5. Let's try 5 first. Make clean and make. Oh yeah, so I also need IO stream here so that I can print things. Any questions, guys? I'm just making this Fibonacci number since we are done with the square root function. But if you have any questions for the square root function, just let me know. You can see it's already coded here. So this is just some extra stuff that I want to do for fun. So make clean and also clear our terminal, then make. What is this saying? Warning constant comparison, integer comparison. int constant. Ah, yep. So I also take this kind of a warnings to be helpful. So what you can do is you can write unsigned long I. That's more proper way, Then make clean, make. Now it should. Oh, it's not printing. Why? Because I did not update uh, my function for this one. This should do it. Make clean. Any new viewers, if you have any questions, just let me know. Hey man, why you are posting sad emoji? Did I do anything wrong? So this is Fibonacci numbers, but why it's incorrect? Not sure. I have to troubleshoot it. I may do it later. I'm kind of exhausted. So with this, I think I just want to end the stream. I will do the Fibo number later. And so yeah, just to summarize what we did today. Man, I'm sorry. I don't have your GitHub link. Is it just your username? I can have a look. No worries. So let's search for your name, GitHub, and story. I'm trying to find your GitHub page, man. Don't be sad. Story. If what profile I'm having in front of my screen is correct, then I think I saw your GitHub page. But I think you haven't posted anything. Am I correct? Or have you posted something? Not sure. So this, I think we will do it later. Let me comment this out. But today, isn't the square root algorithm the binary decomposition method for finding fast square root in log n term, or is there some other implementation you are doing? Yeah, so I know that the square root function that math library provides is quite fast because they already optimize it to quite a degree. But my problem with math library square root function is it's not with constant expression flag on. So this is something new which I did in this live stream. So, and it's not something live under something unique that I did. Lot of people do it. I just wanted to do it myself. So what does this constant expression flag does is it executes your code compile time. So you don't have to wait for binary to create an entire machine code and do it for you. So what you want to make a compile time square, you want to make, yeah, so that's my aim basically. And in this live stream, if you go back, I explained how I did it. I basically use this Newton's method, for which is like a very fast algorithm. It provides a fast conversion, but the problem in Newton's method is it requires an initial guess. and you can't give any random guess, right? It must be some educated guess. So this part does the Newton's method, this for loop, and this one line provides an initial guess. And how I'm doing this initial guess, I'm using this Taylor expansion. So that during the live stream, there was also a question why I'm not using a Taylor expansion and going for Newton's method. The reason is the Taylor expansion is limited for numbers that are less than or equal to 1, as you can see here. If your number is, let's say, 10 or 20, then this expansion will start to diverge. For initial guess, it's quite a good approximation, but if you want to have a accuracy with higher digits, then you have to go for, at least from what I understood, this is what you have to do, this Newton's method. I hope that answered your question. So yeah, so in this live stream we were basically able to achieve writing a power function with any fraction value and any x value. Of course, we are excluding the case where we can have the imaginary root. That's not what I want to deal with right now. And for easy functionality, I also write this square root function where I just pass zero point 0.5 argument to our power function. And usually in our exponential function, we have this usually in math libraries we have this kind of exponential function, which is basically the power of this number. So this is something we were able to achieve today. In the next live stream, I will shift my focus to global model, because that's kind of my ultimate goal with this project. I want to sorry, where is, oh, let me show you what my ultimate goal is. So where is Wikipedia page? So as I said during the stream, my ultimate goal is to code this global model, and this is something related to my PhD project. So I'm quite motivated to code this, and the entire reason why I need this constant expression flag on is because I can code this entire theory during the compile time. Because just to share you one story, I coded this thing, and I can share with you guys. Yeah, so this global model I already coded previously, but the biggest problem with this global theory is it takes too much time to run. For example, in last run, it took me like one day, more than 24 hours, just to make a simulation. And I learned that this constant expression can evaluate your code during the compile time. So I think that would be quite a speed boost. And the advantage here is, I can show you, I have like 8 cores in my PC. So all these 8 cores can run this code simultaneously. At least that's what I understood. and it can make things faster. So that would be the goal of next live stream, to code this global model. And from now on, it would be more on the physics side. But of course, you guys can join to see how I do things, and also to learn about new coding concepts which I learned during uh, my 5 years of degree. So if you are interested, just join and learn things, because that's the ultimate goal: learn new things. So I hope you guys enjoyed this stream. If you have any final thoughts or any final questions, just let me know before I end the stream. Otherwise, we will say goodbye. I wait for a few seconds, then I will wave hands. I think we don't have any questions left. So let me stop sharing. And with this, I end stream, guys. See you guys tomorrow. Bye. Thank you for joining.